In the previous lesson, we looked at different ways of calculating the total charge depending on the shape and size of your object. So if you have a charged object, it can either have a linear charge density, a surface charge density, or a volume charge density. And from that, you can calculate the total charge of an object. So what if we wanted to calculate the total contribution from that object and figure out an electric field? So what if we wanted to calculate the electric field from distributed charges? So in that case, instead of looking at dq, we're going to have to look at dE. So that means a differential electric field element, which is going to be defined by your dq over r. And that's where that equation comes in handy, because in order to calculate dE, we're going to integrate it and be able to calculate the total electric field at a point P away from that object. In this section, we're going to take a look at how we would calculate the total electric field at a certain point P away from some volume of arbitrary shape. So, in other words, why don't we start by drawing a shape. This nice shape. I'm going to say that this is an arbitrary shape, and we are trying to find the total electric field E at a point P away from this volume. So in other words, if we have a point P over here, let's see, we'll call this point P. That means that I'm also going to have some sort of differential volume element here, which we've drawn before in the previous section. Let's just draw it again here. We have this cube-like shape, or a section of the volume, which we'll call dV. And this dV has a charge dq. And we'll see this charge dq and also this differential volume mass element is at an arbitrary point A on the shape. So now, this point A is a direct distance r away from this point. So there's going to be some sort of unit vector, r hat, going from this arbitrary point to a point P. And at this point P, it's going to experience an electric field. So there's going to be an electric field pointing this way. We'll just say away from that arbitrary point, and we call this the differential element, or a differential electric field element. So now the problem is we're going to have tons of these orange blocks all over this arbitrary shape, and that means R is going to change, and also the value of dE is going to change. So right now I want to say that in orange, let's say at some arbitrary point A with dV there is a, we'll call this a baby charge, dQ, that creates a baby electric field called dE at point P. And then the distance between the dv and dE elements is r, is r with r hat pointing towards point P. Okay, so I've color-coded each of these, and now what we want to do is try and figure out the differential electric field. So we want to figure out a way to quantify dE. So then the differential electric field element is dE is equal to, remember we have kq over r squared for our equation for electric field, but in this case we don't have total charge q, we have a baby charge dq that corresponds to the baby electric field. So we have k dq over r squared in the direction of r hat. And because this is a volume, we know that dq can be rewritten as, so remember, dq was the volume charge density times dv. So we can write this as k rho v dv divided by r squared r hat. So that is the equation for the differential electric field element. So to calculate the total electric field, this is where all of our training and integration comes in. We're going to need to take the integral with respect to volume of dE. And you know, this example has to do with the volume. If you have a surface area, you take the integral with respect to surface area, and if you have a linear quantity, then you take the singular integral of that. So in this case, we're taking the integral of dE with respect to volume, which is the integral of k rho v dv divided by r squared r hat. And just keep in mind that it isn't just as simple as doing this integral, it's this part that's troublesome. R hat. The distance that dv is away from a point P is always going to be different depending on where you are in space. So I want to say be careful, because E is a vector quantity. So we must consider dex, dey, as well as dez, and each of these will give us the electric field in the x direction, y direction, and z direction. So x, y hat, and z hat directions. And then at the end, you would just get the magnitudes of each one, and then your E would be equal to EX in the x direction plus EY in the y direction plus EZ in the z direction. And so this is where it comes, this is where being able to read the question choose the correct coordinate system and choose the correct spot to place your origin comes in handy. Because if you put your origin in the correct spot and you look at symmetry, you might just be able to cancel out a couple of these so that you can simplify the number of integrals that you do. So we're going to do that through a whole bunch of practice problems later on.